to present some new results that we have about quantum teleportation. So quantum teleportation does it in production. So is it good for you? So why quantum teleportation again, right? So this is a pretty old protocol. Everyone knows about quantum teleportation, of course. But so what I will talk to you today, so I will try to show to you that there are still some new things that we can say about teleportation, or at least on the teleportation scenario. Let's put this way. So we have this teleportation that is a pretty simple protocol, right? So it's why is this so important, right? So it's a protocol that it's extremely simple to explain. So it's one of the first protocols that we learn when we learn quantum information. So, but at the same time, it's a protocol that's extremely difficult to perform in the lab, right? An experiment. And there are many reasons for that. So one of the reasons that, so in teleportation, we try to achieve several things. So one is the possibility of preparing arbitrary states, the states that we want to teleport. The second thing is that in teleportation, so one of the goals is to perform teleportation over large distances. So we want to be able to produce entanglement between large distant laboratories. And we also need these entangling measurements, right? The Bell state measurement, or a measurement that is able to transmit information from one side to the other. And achieving these three steps at the same time is extremely challenging for experimentalists. So here you see that, so we have several setups that people consider for teleportation. And each one of the setups has its own advantages and disadvantages. So you see that in terms of distances, teleportation were achieved for more than 100 kilometers, or many times on optical tables. And in different types of systems, like in atomic ensembles, trapped atom, solid state system, photonic qubits, and so on. And so in order to certify the quality of the teleportation, what is usually used is this average fidelity of teleportation. So I think most of you are familiar with this. So this is simply how well the teleported states, how similar the teleported states are to the input states, the states that we want to teleport. Right? So many times this figure of merit is used to certify the quality of the teleportation, and it's also used to certify the quantumness of the setup. Right? So we want to, if we achieve, so it's known that if you achieve high fidelity of teleportations, because your protocol is performing like a, so your protocol is really quantum, right? So what we want to do is to prove that you can do teleportation better than any classical protocol. So many times this figure of merit is used to certify how quantum your setup is. And what is known about this figure of merit is that according to it, not every entangled state is useful for quantum teleportation. So there exist states for which, so no matter what you do with this state, you'll never be able to teleport better than the best classical protocol. An example of these states are bound entangled states, or states with low singlet fidelity. So you need to have certain amount of entanglement in order to perform quantum teleportation. So what I want to discuss here is a new benchmark for certifying that teleportation that happened is non-classical, right? So there is no classical protocol that is able to do what the teleportation is doing, what your protocol is doing. And according to this new benchmark, as you see, so now with this new benchmark, it's possible to prove that every entangled state can be used as a teleportation channel that is non-classical, right? That has no classical equivalent. Right, so this is the outlook of the talk. So first I will say some words about teleportation, and I will put teleportation in the scenario that I want to that makes it more clear what I want to explain. And then, so I will show this new benchmark, which is a way of certifying non-classical teleportation that uses the full data available in a teleportation experiment. And then later on, I will discuss a little bit, so this idea of that every entangled state can can be used as a non-classical teleportation channel. And finally, I will discuss the connection of this non-classical teleportation with other tasks like quantum steering and the nonlocality. Okay, let's start with teleportation. So teleportation can be put in the following way, okay? So we have a verifier that would like to verify that Alice can teleport states to board. So this verifier sends input, so systems in a given state to Alice and asks Alice to teleport these quantum states to board. Then Alice performs some measurement on the input state and the share of the state that she has with Bob. And then later on, Bob sends these, so the post-measured states back to the verifier. Right? And what the verifier does usually is to compute this average fidelity of teleportation, which, as I said, is simply the average fidelity of the output states here with the input states that he sent to Alice. And depending on the output that Alice gives, so the verifier has to apply a correction. Right? So I think everyone knows this, no? So if this is a bare state measurement, right? So what happens that if this, so in the ideal case, right? So where the state shared is a maximally entangled state and the measurements are a bare state measurement, every state here will be exactly the same as psi x, and then this average fidelity of teleportation will be equal to 1. So, of course, in the non-ideal case, for example, if the measurement is not a perfect entangling measurement and the state shared is not a perfectly maximally entangled state, so we will have this average fidelity below 1, right? And usually the goal is to achieve a certain value that is higher than the value that could be achieved by any classical protocol. And just to give you an example, if we are talking about teleporting qubits, this classical fidelity is 2/3. Right? So it turns out that if you go to the lab, perform the experiment, and find this above 2/3, it's because your teleportation experiment is doing something that is genuinely quantum. So as I said before, so not all entangled states are useful for this in the sense that there exist entangled states for which no matter what you do with them, you will never be able to beat this classical limit, right? For example, bound entangled states, right? So this class, so you can compute the classical limit for any prior, right? So any prior. No? Yes, sure. Maybe if you are using, okay, the Haar measure, yes. Yes, here there are two things. Yes, okay. Usually these bounds are computed by, so if you want to teleport all states, all pure states, for example, right? But you can also compute all these bounds if you want to teleport, let's say, a finite set of states, and all these things will change. This result by the Autodesk is when the prior is the Haar measure. Yes. But yes, for other priors, I don't know if you can do it. All right. So, okay, but then let's see what is the, okay. So our motivation to make this study was to realize that, okay, so this average fidelity of teleportation is actually a cost grain measure, right? So you are reducing everything for a single number. So we want to see, so first of all, let me show one possible protocol that achieves this classical value. That's a classical protocol that achieves this value, okay? So let's see what happens in this protocol. So suppose that we are here teleporting qubits, and then so the verifier sends states, let's say, pointing in a given direction of the Blois field. So one possible protocol to achieve these two-thirds classical is the following. Alice applies a measurement in a given direction, say the z direction here, right? And then if she gets this outcome plus here, so Bob prepares this state 0 and sends back to the verifier. And if she gets the state minus, Bob prepares this state 1 and sends back to the verifier. Okay? So if you make the calculation of the average fidelity of teleportation here, you find two-thirds, right? So in the case that, so the verifier is sending any possible state in the plus field. So, but you see that even if they achieve two-thirds, so the states that the verifier will receive can only be two, 0, 1, right? So the verifier always receives either 0, 1, no matter which direction he sends. Right? So of course the average fidelity of teleportation is two-thirds, but the verifier can check that everything is classical, right? So he's only receiving two possible states no matter which direction he sends. Right? So this was the motivation, right? So actually the two-thirds is achieved, but the teleported states, so that you would expect in a typical experiment, are not simulated by this classical protocol. So, and then, so this is just to realize that the fact that you got the average fidelity of teleportation below the classical bound doesn't imply that the protocol can be classically simulated. Doesn't imply that there exists a classical protocol that simulates exactly the output of your experiment. So again, this is because we have more information in the experiment than simply this number that is the average fidelity of teleportation. So, and then, so this is the question that we wanted to address. So can the experimental data, so the whole data in your experiment, be classically simulated? Is there any classical protocol that simulates what you see in the experiment? So, okay, let me show you a way of certifying that the teleportation data is non-classical. So let's see how the verifier can deal with this problem, right? So from the verifier point of view, what happens is that he's sending inputs in a given state and receiving these outputs with a given probability, right? But he doesn't know anything of what is happening here inside. And what he wants to show is that what is really happening here is genuinely quantum. For example, he wants to show that what Alice is doing here is sending states using entanglement, Alice and Bob. So what he knows is that so the output states are given by, so Alice and Bob, they share this rho AB that the verifier doesn't know, and there is this state that he sends, and then inside this box there is a measurement happening, right? And this measurement is happening in the input that he sends and the half of this rho AB. So what you can see is that, so by tracing A here, I simply trace A here, you can see that this can be written as simply as this equation here, that is simply telling you that the output states that the verifier sees is given by this input state being sent through a channel. Nothing surprising here. But what is interesting to see is that now we want to see what are the properties of this channel if the state shared by Alice and Bob is separable. And it's not difficult to see that if the state here is separable, this effective channel here will be separable again, right? So there is no entanglement between Alice and Bob. This channel has to be a separable channel. There is no use. And then, so another interesting thing is that although we started here with a separable state and showed that this effective channel is a separable channel, we could also think of this channel as some sort of local hidden classical channel. So you could think as this teleportation here, through this classical teleportation, as a protocol that with a given probability, like gets this classical variable lambda, right, sends to Alice, and Alice, upon seeing the value of lambda, applies this local measurement on her share of the state. And Bob produces this state rho lambda and sends back to the reference. Okay? So you can see that this is a purely classical channel or purely classical protocol that only needs this shared classical variable lambda. But with this now I can propose a protocol, so a figure of merit that tests if a given protocol is quantum, right? Is using entanglement. So the idea is that, so from the verifier point of view, what he wants to solve is this problem. So given that he sent these states and obtained these states, he tries to find like a channel operators, right? Which transforms the input state into the output states, and such that these channel operators are separable, right? So if he solves this problem and cannot find any separable states that transforms this set of input states to the set of output states, is because entanglement had to be used, right? So the only technical problem here is that enforcing that a given operators are separable, we all know that in general so this is a difficult problem. So what we can do here is to relax this condition and impose, for example, that these operators here are PPT, so have positive partial transposition. Or you can impose that they are K-shareable, for those who know. But this is just a relaxation of the separable set, which we can deal kind of easily numerically. So, and as I said, with only this information, if the verifier solves this problem and finds no solution, so if there are no set of channel operators which solves this problem, is because the teleportation is non-classical. So the advantage of this is that so it can be solved by semi-definite programming in general. So if you apply these relaxations, so it uses the full information about the teleportation experiment, right? So it uses all the set of input states and all the set of output states, and actually it's valid for any prior, right? So as Miguel said, in principle, so in teleportation you don't need to let's say, suppose we want to teleport only 2 or 3 or 4 states, right? So in general, it's not easy to compute this average classical fidelity of teleportation for weird priors. And so here we can do, so easily we can fit so this problem here for any prior, right? Because it only depends on the set of input states and the output states that you see. And another good thing about this is that so every semi-definite programming has a dual formulation, right? That you can understand in terms of these teleportation witnesses, right? So these teleportation witnesses are simply linear constraints or semi-definite constraints on this, like that depends on the set of inputs and the set of output states, which you guarantee that so this function here is positive whenever the teleportation is classical, which means that so you go to the lab and you apply this. So if you have a witness, you apply the witness and you see a negative value, it's because the teleportation is not classical, right? So again, so you can, it's similar to the case of separability, right? Where you have a set of separable states and you have, if your state is entangled, there will be an entanglement witness. Here is similar. But here we have a set of classically simulatable data, right? And if your data is non-classical, there will be this teleportation witness that separates the set from your data. So let me show you an example to be a bit less abstract. So the simplest example here, right? So let me consider a Werner state, which is simply a convex combination of a maximally entangled state and white noise. So suppose we want to teleport, let's say, all the eigenvectors of the Pauli matrix, right? And suppose we apply a Bell state measurement, okay? The simplest scenario of teleportation. So if you do this, if you solve this problem, right? So you find this teleportation witness here. So those are these operators that I have to put in my teleportation witness, and you see that they are simply given by like measuring again the Pauli matrices X, Y, and Z. And if you compute the value of this witness for this teleportation data, you find this number, which is negative whenever P is above 1/3. Right? And this 1/3 bound is simply the separability bound. Right? So you see that for all Werner states, we can certify that they provide this non-classical teleportation data. So, and then of course this motivates us to ask which states can be used to provide this non-classical teleportation data, right? And so I'm not going to enter into details here. We can discuss later if you want. But the idea is pretty simple. The idea is to show that for every entangled state, right, there is a set of input states that the verifier can send and some entangling measurements that Alice can perform, such that the data will be non-classical. Right? There exists a way of showing that this state provides non-classical teleportation. Analytically, yes. So, and the idea is pretty simple again. So the idea is that, it's easy to see, no, not easy, but so it's possible to see that if the set of states here are tomographically complete, and Alice applies a Bell state measurement, so these data here will be non-classical. Okay, so this is how we are doing this. So this means that it's possible to prove analytically, but so if this is the case, you put these in the SDP, and the SDP will tell you that it's non-classical. And one way of showing this analytically is by this robustness of teleportation. So I think this is interesting because this also kind of quantifies how non-classical the data is. So you can ask, given a teleportation data, how much noise you need to add to this data in order to make this post-processed data classical. Right? And this is similar to the robustness of entanglement, where you have a state that is entangled. You can ask how much noise I need to put in this state such that it becomes separable. Right? And then, so it's possible to see analytically that the amount, so if the set of inputs is tomographically complete and the measurement is a Bell state measurement, the amount of noise that you need to put in the teleportation data is exactly the amount of noise that you need to put in the state such that it becomes separable. This means that for every entangled state, so for which the robustness of entanglement is non-zero, the robustness of teleportation will be non-zero as well. So this says that if the set of inputs is tomographically complete and the measurement is a Bell state measurement, so we get non-classical teleportation for all entangled states. But also, it's another interesting thing that happens here is that, so this is the case even if the measurement that Alice applies is a partial Bell state measurement. So, and this is interesting, especially for experimentalists working on linear optics. So you know that with linear optics, it's not possible to make a complete Bell state measurement, right? So, but in this case, even by using these partial Bell state measurements, it is possible to certify non-classical teleportation from all entangled states. So, just to give you another example, so before I said that using the average fidelity of teleportation, bound entangled states are useless in the sense that they will never surpass the classical bound, right? So let me give you an example of a bound entangled state. So this state, believe me, is bound entangled. So this is a well-known example of bound entangled states based on an extendable product basis. So we consider this set of inputs. So you have to believe me, they are tomographically complete. And we impose that the measurement performed by Alice is tomographically complete, right? And what you get, so the measurement is a partial Bell state measurement. And what you get is these witnesses, where each one of these states here is actually one of these input states here, right? So, and then you find this tiny little negative number here, which shows that so we get a value. Yes. Yeah, because this is the bad output. As well. Yes, so you only need that you have one good outcome, the rest you don't care, because you can always fix these witness operators here to 0 whenever you have this bad outcome. What happens is that, so if your prior is not tomographically complete, okay, so there will be some states that you fail to detect. But okay, you what you can do is to put in the SDP and see if it's a good set of priors for your state or not. The fidelity for, okay, this I don't know. The fidelity of a bound entangled state for arbitrary priors, I don't know, and this is actually not easy to compute as well. So Miguel has a paper on this to compute the classical bound, I mean. Yeah. Right, so this is also a difficult problem. How to compute the classical bounds if you have an arbitrary state and arbitrary priors. So it can also be done by SDPs and so on. Okay, and so we are now collaborating with the group of Fabio, who is around here. So this is still under development, but what we want to show here in this experiment is to show an example of a state that could never show quantum teleportation using this average fidelity of teleportation, but for which we can detect using this new figure of merit here. So the sketch of the experimental setup is this. So they have two sources of entangled photons in polarization. So one of these sources used by the verifier to prepare different states to Alice here, right? So those are these polarization measurements. And the other source is used to distribute the entanglement between Alice and Werner. And this setup here, this shared state preparator, is there to prepare this state here, right? So this state that we want to prepare is a convex combination of a singlet state and this state VV, okay, vertical polarization to both photons. And the way, so the idea that they came up to produce this state is the following, right? So first they produce the state, the singlet state, and then in one of the photons they put this calcite element here, which splits the path of the photon depending on its polarization. Okay? So if the photon is H polarized, it goes through. If it's V polarized, it deviates a little bit here. Okay? And then they put this half-wave plate here to rotate the polarization of the photon, such that if the photon is V, its H it becomes V. If it's V, it becomes H. And now by putting this another calcite here, so they make the photons go in the same path again. Okay? And then they apply a rotation that in this case does nothing, right? So I have a V polarization and H polarization. It just changes V to H and H to V. So in this case, you can see that the setup, if you send a singlet state, the output is a singlet state. It does nothing. But now, by changing the angle of this half-wave plate here, right? So this is for half-wave plate of 45 degrees, but if they put at 0 degrees here, what happens that, so again, so if it's H, it goes through, if it's V, it deviates here. But now it does nothing with the polarization, right? If it's H, it keeps being H, and if it's V, it's V. And then the H goes through again and is rotated here, right? While the V is sent out, right? So we ignore this possibility here. So you see that if this angle here is 0, so the singlet here is transformed into VV, right? Which is this. And so we wanted to use this state because if you compute the average fidelity of teleportation for this state as a function of P, you see that if P is 1/2, it becomes below the classical bound. It's below 2/3. But now, if we compute this, the violation of the teleportation witness that comes from this state, you see that we violate this witness for the whole range of P. Yes. So you can see that. So if you have VV, right? So the average fidelity of teleportation. So you are right on the classical limit again, right? So it goes down because here we have HV plus VH, right? So then it teleports well, but you are adding noise, which is in an orthogonal subspace, right? But when you approach this noise, it becomes good again, because you are right in the limit of being in the classical limit. Yes. so you can also see this. No? At this point here, you have to change the set of unitaries that makes the teleportation better for this state here. So, and finally, let me discuss the connection of this idea of non-classical teleportation with steering and this idea of Werner equality with quantum inputs. So in steering is a situation that's pretty similar, where the verifier wants to detect entanglement between Alice and Bob. Again, he doesn't know the state of Alice and Bob, and he doesn't know the measurement that Alice is performing, but he can send classical inputs to Alice. So he tells Alice, apply this measurement or apply that measurement. Okay, so this classical choice of inputs. And as we know, so in steering, not every entangled state can demonstrate, so can be detected here. Okay, not every entangled state can demonstrate EPR steering. And you can see now that what we are doing here in teleportation is simply changing these classical inputs to these quantum inputs. So instead of simply telling Alice, okay, make this measurement or that measurement, so the verifier encodes this classical knowledge in the quantum state of the system and sends to Alice. So, and because of this, now it's possible to show that every entangled state here can be detected. So, and this is also very similar to what happens when you have also Bob, which is also black box, let's say. So Bob also applies a measurement that is not known by the referee, but the referee also sends a set of inputs, quantum inputs here. So there is a bunch of papers. So this was first proposed by Buscemi, and then the group of Nicolas Gizan, Danny is on these papers here. So they developed these and also got these ideas of like this measurement device independent witnesses, right? So witness to detect entanglement that do not depend on the specific form of the measurements being applied. And again here, every entangled state can be detected. And to be honest, from these proofs here, we could already see that in the classical case, we would obtain non-classical teleportation for every entangled state, right? Because what we are doing in the teleportation case is simply removing these measurements here and applying some sort of tomography here, right? So we could apply all the proofs here. So the idea here is to show that, so to show a way of demonstrating with the data that we have, so that is based on the tomography here, how to detect this non-classical. And so just to conclude, so the idea was to show a method for certify that the teleportation process is non-classical, right? So a method that is experimentally friendly, and this method uses the full data in a teleportation experiment. So it uses the full set of input states and output states. It works for any set of inputs, right? So for any set of inputs, you can try to solve this SDP. It gives this idea of non-classical teleportation witnesses that is very useful for experimentalists, right? And so it can be used as a benchmark for quantum technologies in the sense that you can use it to certify that your experiment is doing something that is really quantum. And we can also apply ideas like robustness to noise and these kind of things to see how quantum these setups are. So we could show that non-classical teleportation can be detected from any entangled state and even a partial Bell state measurement, which is also very useful experimentalists. And so in the future, we want to work more on the quantification of this non-classical teleportation. So we are working on this multipartite scenario. We can extend these ideas to networks, for example, where in some of the nodes we can probe the nodes with quantum inputs. Some others we can make tomography, for example. So we are still struggling on this, but I think this is a nice theory problem. So for those who know a bit about steering has a deep connection with this idea of joint measurability, of the measurements that Alice applies being also quantum, right? So somehow we are also checking the quantumness of this measurement that Alice applies, right? So in steering we have this notion. So here I don't know what would be the notion. So this quantumness of the measurements in the teleportation scenario. And of course, so experiments, we are collaborating with Fabio and